Hi, I'm Maciek and I'm Cloud Software Engineer in SPDK team. Today, I'd like to show you something called Dynamic Scheduler, of which you could already hear about in Jim's State of the Project presentation. First, I will talk shortly about Event Framework, threads, and pollers to get basic knowledge required to understand schedulers. Then I will talk about static and dynamic scheduler and show you how they work and how can we benefit from schedulers. But before I get to that, let me talk about basics first. As most of you probably know, SPDK by default works in a pull mode. This means that we don't rely on interrupts, but we pull events. This is one of the reasons why SPDK has such a good performance, but it comes with a drawback. Let me show you what I mean by running htop application. As you can see, my machine is quite idle right now. Now let me run SPDK target application in the background. Now you can notice that cores used by SPDK take 100% of a core time. This is because we are polling in infinite loop without any breaks. But does this mean that SPDK is using all of the CPU time to do some useful processing all the time? Not really. To actually get to know what SPDK is currently doing, I will run SPDK top tool, which demo presentation was done by Krzysztof. Okay, let's do a quick recall how threads and pollers work in SPDK to understand better what we see on the screen. SPDK creates one reactor per core that it will be using. Each reactor has infinite loop which calls reactor run function on each iteration. SPDK uses lightweight threads with pollers registered on top of them, which are polled in a defined way. We could register active pollers that are called on each SPDK reactor run, or we can register timed pollers, which are run in predefined time periods. Each poller can do some processing if some request or event is pending, or they can just check that no processing is required and return. In first case, we say that poller did some work, so it was busy. In second case, it basically didn't do any processing, so we say it was idle. That busy idle logic transfers to threads. In case no poller within particular thread didn't do any processing, we say that thread was idle. Otherwise, it was busy. For more details on this topic, I invite you to read SPDK documentation on our website or visit SPDK YouTube channel where you can find presentation from 2019 done by my colleagues Darek Stojacik and Ben Walker, where Ben dives into details of what I'm talking about right now. Okay, now let's check that in SPDK top tool. Let me switch to Cores tab. SPDK is using currently 8 cores. When I select a core, you can see that there is one thread pulled on this core. Now, when I select that thread, you can notice that it has two registered pollers. Now, let's move to Pollers tab. From status column, we can tell that almost all pollers are currently idle. Let's check Threads tab now. Because of all pollers are idle, threads are idle as well, which you can tell by comparing busy and idle times of a thread. Now let me make SPDK do some processing by starting some I/O traffic in the background. Now some of the threads are busy most of the time. In Pollers tab, you can see that this is caused by pollers doing some processing and therefore being busy. So now SPDK is actually doing a hard work. But if I stop I/O traffic, everything is idle again and SPDK is not doing any processing besides polling and waiting for events. But from CPU perspective, we are still using 100% of a core time, which you can check in htop tool. So it does not matter if we are processing something or idling. We still use 100% of a core time. This is where dynamic scheduler idea comes to life. But before we can talk about dynamic scheduler, we have to get know what static scheduler in SPDK is. We use it to distribute threads to cores. A scheduler decides on which core thread will be placed. This can be limited by a core mask of a thread. It defines on which cores scheduler can place a thread. Core mask can allow it to one core, multiple cores, or all of them. And it will be up to scheduler which of the allowed core from core mask it will select to put new thread on. By default, SPDK uses static scheduler, which uses round-robin method to select on which core place a thread, but it still has to be core from core mask defined for this thread. As you can see, threads are spread across cores quite evenly. Currently, they are idle most of the time because we are not getting any events right now. So, do I need that many cores polling at the moment? That does not look like optimal resources usage, and there isn't much that I can do about it. Or maybe there is something. So what if I want to have different behavior or even more control over threads placement? In SPDK, we can actually add new schedulers as a plugins and switch between them. Schedulers can do much more than the default static scheduler. The good example is Dynamic Scheduler, currently implemented in SPDK as a plugin that user can enable, replacing static one. The purpose of it is to save resources, but do not lose the performance. There are simple rules in Dynamic Scheduler. First rule, if a thread is idle, move it to the main SPDK core. Second rule, if a thread becomes busy, move it to another core compliant with core mask of this thread. Third rule, we can use main core for busy thread if its load is low enough. Fourth rule, probably the most important rule in the current state of implementation, we can switch core mode from poll mode to interrupt mode if it does not have any threads present. Yeah, that's correct. We can switch unused cores to interrupt mode, which I will talk about in a minute, which means we will stop polling and free cores load. This way, in case SPDK does not do constant processing, we can reduce number of resources it consumes and still have the same performance. Let me show you now how all of that works. Now I enabled dynamic scheduler in our SPDK target with no I/O processing being done. As you can see, most threads are quite idle now. Let's move to cores tab. All threads were moved to the main SPDK core. This is where the first rule of dynamic scheduler works. Let's look at htop interface. You can see that all cores used previously by SPDK except its main core are now idle. This is because they don't have any SPDK threads and were switched to interrupt mode in SPDK, the fourth rule of dynamic scheduler. This means we stopped reactor run loop on those cores. This is where we get all the savings. This way we consume less power. But what will happen if I start some I/O processing now? Let's say I want to start 4 new I/O transactions. As you can notice in Threads tab, some of the threads are very busy now and have been moved to another course. When we look at htop, we can see that 4 cores that busy threads were moved to are now back in poll mode and they are busy again. And other cores stay in interrupt mode. That's the second rule of the dynamic scheduler applied. Because of that, we are back to full performance mode. but only as much as it is required at this particular moment. So in this case, 4 additional active cores is enough to get full performance, and other cores assigned to SPDK contribute to lowering power consumption, which won't be possible with static scheduler, which would be polling all 8 cores. When I stop IO traffic, you can notice that threads become idle and they are moved back to the main SPDK core, and rest of cores are being switched back to interrupt mode to save cores time and in result save even more resources. But this is only the beginning of what the dynamic scheduler would be able to do in the future. Imagine a serve scenario where we have light I/O traffic that causes low core load from SPDK point of view. In such case, we could actually move 2 or more threads to one core, keeping the same performance level, and because of that, we'll use less amount of cores and get more resources freed. We are currently working on implementing such algorithm in Dynamic Scheduler and many more improvements, so stay tuned. I also invite you to write your own scheduler plugin suitable to your environment model and sharing it with community. Okay, so let's summarize what we just watched. SPDK provides interface for user-defined schedulers. By default, it uses static scheduler, which gives us top performance, but takes maximum resources assigned to SPDK. SPDK also provides alternative one called dynamic scheduler. From user point of view, it can provide similar level of a performance as a static version, and at the same time it can save some resources if more of them are assigned than it is needed at a particular moment. I hope that this demo showed you that SPDK can have not only an excellent performance, but it can also save your resources, so basically save your money. If you have any questions, we'll host Q&A after last demo, and feel free to write your questions in the chat window. Thank you for your attention. I hope you enjoyed it.